For decades, the story told about this place claimed that microphones lowered into the shaft recorded the screams of tortured voices rising from below, and that Soviet drillers had broken through into some kind of chamber of fire and suffering. There is no recording. There is no chamber. No credible transcript exists. No scientist on record ever made that claim, and no equipment used at the site was ever built to capture anything of the sort. The story survives because it is easier to accept than what the instruments actually measured. The verified record describes something else entirely, an ancient, compressed body of rock that stopped behaving like a solid, a shaft that closed itself shut behind the retreating drill bit, and a temperature that climbed far past every model built to predict it. Nothing needed to be invented. What actually happened 12,262 meters beneath the Kola Peninsula is disturbing enough on its own terms. The project began in 1970 in the Russian Arctic, under the direction of Soviet scientists who had no interest in oil or natural gas. Their target was the crust itself, the physical material beneath the seismic charts, retrieved as core rather than inferred from an equation. Over the following 2 decades, the shaft descended past the depth of any well drilled before it, and it has not been surpassed since. Set the tallest building ever constructed end to end against this shaft, and it would need to repeat itself roughly 15 times just to reach the bottom. The hole itself never widened beyond roughly 9 inches across, a shaft the width of a dinner plate.
Sunk in a straight line through rock dated to 2.7 billion years of age.
To sustain that descent, Soviet engineers deployed the Uralmash 15,000, a rig weighing in at 15,000 tons, replacing an earlier and far less capable machine. Conventional rotary rigs turn the entire pipe string from the surface, but at these depths, that method destroys itself through friction and torque before it ever reaches useful depth. Engineers instead fitted a hydro-turbine motor measuring 46 meters in length just above the bit, so that only the cutting head rotated while 12 kilometers of stationary aluminum alloy pipe hung above it, an alloy chosen for its light weight, but for its unexpected elasticity, the string itself measurably lengthening under its own load whenever it was lifted. Even before reaching extreme depth, the abrasive Archean granite ground down carbide cutting heads at a pace that demanded constant tripping, pulling the entire pipe string out simply to replace a bit already reduced to a blunted stub. Friction against the borehole walls eventually climbed to as much as 65% of the string's total weight, and below 7 kilometers, the crew was repeatedly forced to abandon jammed sections and cut new deflected paths around them, eventually drilling 5 separate branching shafts in pursuit of one continuous line downward. Seismic models had predicted a boundary near 7 kilometers, the so-called Conrad discontinuity, where granite was expected to give way to a denser layer of basalt. It never appeared. The drill continued through granite gneiss all the way to final depth, and the boundary long assumed to mark a change in rock type turned out to be something else, a zone of fracturing, mineral compaction, and trapped fluid that merely mimicked the seismic signature of basalt without ever containing any of it. Decades of surface modeling had misread the crust from a distance. At 6.7 kilometers, the core brought up something stranger still, the preserved remains of microscopic plankton, intact despite regional heat and pressure that should have destroyed them, shielded inside mineral casings that had locked them in place since the Precambrian. Water moved freely through rock that theory said should have been sealed dry under that much confining stress. every assumption about a still, layered, predictable crust failed against the sample actually in hand.
The heat was the one variable that was supposed to stay manageable. Planners expected a steady gradient of roughly 11 degrees for every kilometer of depth, arriving at a projected bottom hole temperature near 100 degrees at final depth. Warm, but well within tolerance for the equipment. Below 3,000 meters, that curve broke. The gradient steepened far beyond the model, and the deeper the bit went, the faster the temperature climbed, with no floor in sight and no correction available. At the final vertical depth of 12,262 meters, the measured temperature had reached 180 degrees, nearly double the original estimate, with later readings at the bottom of the hole climbing as high as 212 to 220 degrees. Under that heat, combined with a confining pressure of roughly 336.8 megapascals, more than 3,000 times ordinary surface pressure, the Archean rock at the bottom of the hole, 2.7 billion years old, stopped behaving like a solid. It moved instead like a dense, sticky, semi-molten gel, closing in on itself the instant the drill was withdrawn, squeezing the 9-inch shaft narrower and trapping and deforming the carbide bits left inside it. The aluminum pipe string, heated and stressed near its limits, stretched nearly 50 meters during a single lifting operation, while pockets of vapor disrupted the drilling fluid moving through it. As that fluid rose back toward the surface, it carried something else with it.
From roughly 1 kilometer down to 11 kilometers, the returning mud came up saturated with molecular hydrogen, intensifying sharply past 8.5 kilometers, at times releasing as much as 0.3 cubic meters of gas for every cubic meter of rock drilled. This was ordinary chemistry pushed to an extraordinary extreme. Iron-bearing minerals reacting with trapped water at depth in a process called serpentinization, releasing hydrogen that stayed compressed while confined, and then violently expanded the instant it reached atmospheric pressure at the surface, foaming and hissing out of the returning mud. The crust at the bottom of this hole was not empty, and it was not still. It was reacting, moving, and closing around the instrument sent down to measure it.
No single catastrophic blowout ended the project. The hole simply became impossible to keep open. Rock that flowed like plastic the moment pressure was released would not hold a stable bore. Bits kept seizing, and the margin between what the aluminum string could survive and what the crust demanded of it kept narrowing with every attempt. Layered onto that mechanical defeat came a second and more final one, the collapse of the government funding the work. By the early 1990s, drilling had stopped, and the site was left standing, sealed in the Russian Arctic. It was not an isolated failure. Halfway across the continent, the German KTB project reached its own limit at a far shallower depth, 9,101 meters, when temperatures crossed 265 degrees. 2 national programs, 2 different rock formations, and the same ceiling. The deep crust does not negotiate with drill bits. 12,262 meters is the deepest a drill bit has ever traveled into solid ground, a record that has now stood for decades. Set against the roughly 6,371 kilometers separating the surface from the planet's core, that entire achievement accounts for a distance too thin to register as more than a fraction of 1% of the way down. Every ton of steel, every hydro turbine, every year of state funding purchased access to a scratch on the outer skin of a body that has been cooling, folding, and reacting for 4.5 billion years.
without any need for an audience. The rock did not resist out of hostility. It simply continued behaving as it always had, indifferent to the 15,000-ton machine pressed against it, indifferent to the nation that built it, indifferent to the record it still holds. What the Kola borehole ultimately measured was not the temperature of the Earth. It was the exact point at which human ambition ran out of material that would still hold its shape.